Chapter 5 is all about the network layer. And just to recap, so we can put things back into perspective, for the last couple of chapters, Chapter 3 and Chapter 4, we've been talking about the OSI model, and we've been looking at each of the particular layers. Layer 7 was the application layer, and that layer's responsibility was to act as an interface between us and our end devices. Produces data. Data is then passed down. We're going to skip over the presentation in the session, and we're just going to go right to the transport layer, which was the layer right before the network layer. And the transport layer takes that data and it breaks it up. What do we call it when we break up the data into pieces? Segments. If we're using TCP, what do we call it if we're using UDP? Datagrams, correct. All right, and regardless, what it allows us to do is it allows us to multiplex different conversations into one continuous stream, so we're using our bandwidth more effectively. This transport layer produces the segment which contains, well, if you're using TCP, a whole bunch of fields. And when do we use TCP? I mean, if you had to choose between TCP or UDP, what would you pick and why would you make that decision? And who makes that decision? Typically, the programmer tends to make that decision. So the programmer wrote this application, and they know what kind of data they're dealing with. And data can fall into two categories, right? It's either content sensitive or it's time sensitive. Give me an example of time sensitive data. Videos, voice. Why are those time sensitive versus content sensitive? Because I know you might be telling me if you're watching a movie, you want to be able to watch the entirety. You can't just miss a part of the movie and expect you to understand the ending. Correct? So you might want to say it's content sensitive. And that could be true, but what if it takes you a year to watch the movie? Would you want to watch it? No. And so we say it's time sensitive more so than content sensitive because a movie's written up into what? 30 frames per second? 24 frames per second? And so if you just multiply that by 60, that gives you how many frames per minute. Multiply that by 6, it gives you how many frames per hour. Multiply it by 2, it's typically how many frames per one movie. Correct? Do you think you'll notice if you miss maybe 10 frames or even 10% of the frames to the whole entire movie?
Maybe not.
No, I mean, folks, if you're getting 30 frames flashed in front of your eyes every second and you're missing 3 frames, no. You have a tolerance level anywhere between about 24 to 30. Anything more than 30, we can't detect it. Anything less than 24, you can detect. Okay? So we build our movies from 24 to 30 frames. Now, I'm not counting video games. Artificial stuff, it takes double. So if you're playing a video game, the frame rate should be 60 frames per second. But for natural images, true color images, we're saying about 30 frames per second. So we use UDP in this case because we say what really matters is that they're there in a timely fashion. So I'm not buffering all the time. So I watch 2 seconds of a film, wait 2 minutes to watch the next 2 seconds. That really takes the enjoyment out of it. Could you imagine telling a joke or watching a funny movie and then you miss the punchline because it took 2 minutes later to get it? So UDP is about getting it there. But UDP can't give you reliability. So what happens when the movie starts getting choppier? Start dropping frames. What's that? You, the user, are going to have to hit refresh or pause the YouTube video and drag back your slider, the timeline. But you're managing that. So UDP only gives us 4 fields. That's the source port, the destination port, the length, and the checksum. The only 2 fields I really care about when it comes to UDP are also the same fields that are in TCP, the source and the destination port addresses. When do we use the source address? And how do we assign that? When a client is initiating a conversation with a server or another client, this client will automatically assign dynamically a source port address to the segment that it's about to ship out. And that could be anywhere between 49,152 all the way up to 65,535. Where did I get those numbers? A port address is 16 bits. 2 raised to 16 is 65,536. But we go from 0 to 65,535. An organization, I'll be asking this in your review. I'll probably be asking it on this Wednesday's exam, known as IANA, basically manages or organizes port addresses. And they have broke that range of port addresses into 3 parts. Well-knowns, which go from 0, 1023, right? Registers, which go from 1024 up to 49,151. And then dynamic. All right, well-knowns are typically used for like open services like HTTP, FTP, POP, SMTP, DNS, DHCP. The reason why we call them well-known is by the end of the semester, you guys better know them, right? In fact, a couple of exam questions I asked for Wednesday is, and you'll see in this review, like what port address does DNS use? What's that? DNS, not HTTP. 53, right? What about DHCP? 67, 68? Yeah, it uses 2 of them, 67 and 68, right? You might want to get to know some of those, okay, folks? Especially before this exam. I do ask them. But regardless, the client assigns the application that's making the request a dynamic address so that when the data comes back, the operating system knows what application is requesting this data. So you can think of it as software identification. In fact, the upper layers have no clue what the transport layer does. And the lower layers have no clue how many applications are making the request. All they're seeing is a continuous stream of data coming from the transport layer. So what's the destination port address used for? If the source port's used to identify the application that the client's using to make a request, what's the destination port used for? Yeah, we don't call that an application, so you're right. That it's to identify what quote-unquote application that the other end device is using. Instead of calling it an application, what do we call it? Protocols are rules to govern it. It runs in the background all the time. Usually runs on a server, daemon or a service, or a process. Right. In fact, that's another question I put in the review that might be seen on this Wednesday's exam. What is the difference between services and applications? You use an application, the application uses a service that's typically ran on a server. Okay, now I say typically, but most modern operating systems are changing that. You guys have a whole bunch of services that are running on the background of these computers right here. And they're not considered servers. But what exactly is a server? Just a piece of equipment dedicated to be running all the time to respond to requests, correct? Can you guys give me a couple of servers that we've set up in this classroom using Packet Tracer? What's that? DHCP server, correct. And what did that service allow us to do for our network? Yeah, basically assigned IP addresses. In fact, when I did this, when I was creating this file last night, I was really hoping that I had a DHCP service, but I didn't. I had to go through all 20 of these or 24 of these devices and configure them so they had an IP address. It wasn't fun. It was very boring. And I kept a tradition. I went from like PC1. I called this 192.168.1.1. Then I went to 2 and called that .2, and then this .3, and so on, right? In Chapter 5, what we're going to learn about is how to divide these LANs so they're broken up into smaller, more manageable pieces to give us better performance. In fact, the whole role of Chapter 5 is focusing around the network layer. Part of Chapter 5 depends on your understanding of Chapter 6 as well, which I'm a little disappointed because you really can't get to Chapter 6 without going through Chapter 5. So I'll be introducing some Chapter 6 theory today and probably tomorrow in class. But the idea is we're focusing on the network layer. The network layer produces a PDU called a... Even though Chapter 5 stuff is not going to be on this week's exam, you guys know the answer to this question. What is the PDU called for a network layer? Packet. Why do you know this question? Because in Chapter 2, the only thing we learned about was the OSI model and the TCP model. In fact, it might be a good idea to know the difference between the TCP/IP model and the OSI model. Remember, they both accomplish the same task. Just how they divide their work up is where they differ. So what does a packet produce? Well, it seems like from here on out, we're going to be talking about addressing. When we got to the transport layer, the big addressing that we were talking about was source and destination port addresses. When we get to the network layer, the addresses that we're going to be talking about are going to be called logical addresses. Logical is something rather different, if you will. Example of a logical address would be an IP address. It's actually one of the most popular ones, but it's not the only form of logical addressing. It will be the only one that we will discover in this course, but AppleTalk is another example of a network layer protocol. Novell's IPX is another one. But this one's the most popular one because it's an open, non-proprietary protocol. Because it's open, it's been accepted by many, many different corporations. And hence, we've been putting it in everything, including our Xbox. And yes, your refrigerator will have a logical address and most likely be able to understand the IP address. Samsung is releasing one the end of this year, 2012. Have you guys seen it? Touchscreen. Yeah, refrige that has an IP address, has a touchscreen on it. In fact, you can get the Wagmans app installed on this refrigerator. Hey, that's all what it's about, right? Technology is becoming cheaper and cheaper. Why not justify paying $5,000 for a refrigerator? Because it has a tablet on there, correct? And if you're thinking about it, yeah, exactly. And if you're thinking about it in your Samsung, what does Samsung also make?
Phones.
Computers, phones, tablets, TVs, correct? So what does Apple not make? Refrigerators, washing machines, dryers. So they're looking at that customer that's a little obsessive and saying, look, I got everything Samsung in my house. So not bad marketing, but regardless, absolutely, our refrigerators, our appliances will have IP addresses. Maybe for managing sake, maybe for convenience sake. But yeah, bang up my washer or my... Gotta reboot my refrigerator. Yeah, that might happen. So we have to ask ourselves, well, as long as Microsoft isn't handling it, we'll be good. As long as we ask ourselves, why are we giving out these IP addresses? What is the role of this layer? Well, it all stems down to this is not a good thing. The fact that I have a lot of devices swarming into this switch and they're trying to communicate is going to degrade my network performance. And hence the name for the network layer. We've got to talk about what exactly makes up a network and how do we break our networks up and keep them still able to communicate with each other, but make them a little bit more user-friendly and a little bit more better to manage. And so the network layer uses logical addressing to create this hierarchical approach to allow us to divide our networks up into smaller subnets, to make them easier to manage, and then to be able to do what we call end-to-end delivery. Who initiates the conversation in a network? The client, right? An end device. You use software. The software uses the hardware to actually ship out the request. So you're initiating this. Where does that request go? It's probably going to go through a series of intermediary devices, but eventually it reaches another end device, correct? So this addressing scheme logical addresses, whether it's IP address or whatever, is designed for end-to-end delivery. Looking at this diagram, that's going to be sort of rather foolish. I mean, it's not that I have to go through any other network because they're all on the same network. How do I know that these end devices are all on the same network? Look at the intermediary device that I'm using to connect them all together. This is a switch. Another review question. A switch is a device just like a hub that's used to connect local devices together, correct? How many devices can I plug into a local area network? Typically depends on how many switches I have and how many ports are on the switch, correct? Could I have added another switch to this local area network and then branched off another 23 or 24 devices off of that? Absolutely. Mm-hmm. When do I stop? Yeah. How many devices could I fit onto this network if I keep on adding switches and switches and switches and I grow it? By the way, it's not a good idea to be doing this. But when do I stop? When I run out of IP addresses. It's absolutely right. Because, folks, we use this address to deliver the message from end-to-end devices. If an end device doesn't have an IP address, it can't communicate on our network, correct? By the way, we're just dumbing this down. There are other delivery methods out there that doesn't use IP addresses, but will still allow you to deliver messages N for M, like point-to-point protocol. Killen?
I know there's more end devices than there are IP addresses possible. So do they do it by location? Like, do they manage?
How many main streets exist in this country? Main streets exist in this country.
Tons.
So what makes our main street unique than another main street?
Geographical location.
Let's look at these addresses. In fact, we usually say one main street. And this is an example of what we call a hierarchical address. I don't know if Corning has a main street, but let's just say they do. And let's say Corning's, the address that we're trying to ship to a packet to is going to be 1 Main Street, Corning, comma, New York 14830. Zip code has 5 digits. Is that right, folks? Mm-hmm. Yeah. These are protocols. You got to follow this. So when we start looking at this, Main Street can be very common. How many Main Streets are actually in Corning now? There should only be 1, right?
I was hoping there's only one.
Yeah, there should only be 1, right? Because if there was 2 Main Streets in Corning, look at the confusion this would cause. Are you on this Main Street or are you on that Main Street? Well, I'm on that Main Street, whatever that Main Street is. There should only be 1 Main Street in Corning. How many Cornings exist in this country? There could be a bunch of them, right? What makes this Corning unique than another Corning in another state?
The geographical location again? New York?
The fact that I'm in New York. Would it make sense to give two cities the same name in 2 states? In fact, what are the rules we've been following? No 2 devices on the same network can have the same IP address, correct? Or the same name. And so a post office stuff is very hierarchical to the fact that we start off with technically country, but we assume that if you're sending something locally, you don't have to add the country in there. But if you're sending something abroad, you must add the country code or the country initials. Then it goes to what? State. And then in each of those states, there's going to be cities. And in each of those cities, there's going to be what? Streets. Now, everybody's asking, where does the zip code come in? What do you and I care about? What makes data easier for us to represent? Using numbers or letters? I mean, your parents gave you guys a name and not a number. correct? They don't say, hey, child number 1, come here. It's easier just to say, Bob, come here, or Nick, come here, than it is child number 1, child number 2. It's easier to name child 1, child 2 that way, but, likewise here. We've automated the system, right? When we're passing messages through, that our scanning system's actually looking for zip codes more than they actually look for city names. The other thing is cities can be much, much larger. In fact, where I'm used to come from, there used to be like 20 zip codes that make up our city. Just like there was like 10 area codes that would make up our city. And so when you want to send a letter down the road, it might be like this 14830 dash some other number. And we call those like boroughs, all right, or districts. But nevertheless, us just using Corning Main Street 1 works just fine for what we do. But then we have to add other things like zip codes for automating the process. In fact, what service have we learned about that actually does this for us when we're trying to access a web page? That takes a name and converts it into a number. This automation. DNS. So when we look at logical addresses, we can see that we have this hierarchy, this segment going on where we break our network up into pieces. How do I do that? Well, the 3 rules that come to breaking a network up, well, I shouldn't say 3 rules. Let's say 3 techniques. It's going to be off of geography. I kept on hearing that. I believe, Tom, you were saying that. Another one's going to be by purpose. And the last one's going to be by ownership or by security. It depends on how you want to dictate that. And I don't want you guys to think that you got to follow one of those 3 techniques. And they are just simply techniques. In fact, you could probably take geography plus purpose and add security in there to make your final decision. Let me just give you an example of how we can use geographical location to represent our networks. I could call this Corning. And then I could call this one Pine City. And call this one down here Mansfield. And I can call this one over here Bath. A lot of distances between those networks, correct? And what defines a local area network? Geographical size. The fact that it's managed by a particular or a single organization or a particular individual. What else? By the size of the number of users. If I was doing this, I wouldn't have the luxury of being able to connect them all to one switch. That is, if I'm following the Ethernet standard, the maximum distance I can have between an end device and an intermediary device is 100 meters. It's about 328 feet, give or take. I think the distance between Bath and Corning is more than 328 feet. So what would I need to do to be able to get these segmented or broken up into tinier pieces, which we call subnetting, subnetted to be able to handle this geographical range? Well, we've been talking about LANs, local area networks, and now we're going to introduce another type of network called a wide area network. And a wide area network is when we take 2 or more networks and connect them together using a particular device. And that device is known as a router. It is an intermediary device that acts as a gateway or a way out of a network onto another network. Now, typically when I'm dividing my networks up, I'm not really focusing on geographical locations. That's because the networks I manage are the ones in my home. So another way of taking my networks and dividing them up is by purpose. How might I take the computers in my house and divide them up? And let's just still use these 4 sections. Now this is a home network. All right, so we have children, adults, By just doing that, this could also introduce some security, some parental controls, correct? By separating these into their own little networks, I can implement a whole new policy with these computers than those computers over there. I would forbid my adults to go on Nickelodeon. But I might. You guys are thinking something else, weren't you? Yeah, Monday, I'll tell you what. But I might permit that for my children to do that. But you know what? What about these two? What would they possibly represent?
Business.
I said it earlier. Let's see, appliances. I don't know. How do you guys spell that? Appliances? Something like that? Help me out there. Is it? Kind of, yeah. We'll see. What else might I have? What other area? Well,
Home
automation, that might fall under appliances. What about fixed devices? Like my server, printers. What else? My router. I know that sounds funny. In fact, I might have a series of routers on my home, and in other classes you guys will learn that you probably want to create VLANs if you're doing it within a smaller geographical locations. But for now, let's just say I have some permanent devices on my network. I have a media server, I have a security server, I have a backup server. I might put them in their own group. I also have printers, routers, scanners, network DVD players, and so on. And I might want to put them over here. Why am I doing this? Why am I taking this network and causing myself more trouble when it's just as simple and cheaper for me to buy one switch and throw them all on there and say, it's fair game? Well, one's inert. Like I said here, I might not allow my adults to have access to Nickelodeon where I might for my kids. This institutes security, right? What else? Well, let me give you this demonstration. For devices to communicate with each other using IP addresses, they need to be able to map these addresses to physical addresses. In fact, in a couple of weeks, we're going to be getting into this next layer called the data link layer. And this layer's all about the physical stuff. In fact, they assign physical addresses to every end device on a network. Every interface card has what we call a MAC address, a media access control address. In this particular scenario, everything's local. I really don't need a gateway to be able to communicate with each other. Two things happen for them to be able to communicate with each other. One, I need to make sure that the packet that I'm sending to the end device, that is, exists on the same physical network as it does in the same logical network. Translation, they both have the same network address. So in tomorrow's class, we're going to be exploring the structure of an IP address and how it's made up of two parts. The second thing is, I must know what the physical address is of that device if it's a local device. The way we find that out is through an Arp request, an address resolution protocol. Folks, we talked about a DNS request and how we said that was a resolution protocol. What do I mean by a resolution protocol? When I basically look up something, right, when I'm translating from one address to another. The address resolution protocol that we've explored was DNS, where we resolved a domain name to an IP address. Arp will take an IP address and resolve it into a physical address. So let me do this using a simulation. I'm going to go over here to PC1. I'm going to go to the desktop, and I'm going to click on the command prompt. And then I'm going to type in arp-a. So let me write this command up so you guys know it. So there's a space between the P and the dash. And when I type that in there, you're going to see I have an empty table. And what this table is going to explore is my IP address. So in this case, it's 192.168.1, and the physical address that represents that. Now, I know who I am, and I know what my physical address is. What I don't know is the person I want to talk to. So if I want to talk to, let me ping 192.168.1.20. I'm going to stop this process. I'm going to send out an Arp request. You can see on my PC I have a green envelope representing that Arp request. Now, depending on where this packet's destined to, I know since they both have the same network address, it's destined to stay in this local area network, I'm going to send this Arp request to my switch, and this switch is going to broadcast to everybody. Why is the switch broadcasting to everybody? Because we talked about the difference between a switch and a hub. And we said the only time a switch has to broadcast to everybody is when it's doing what? When it's building its MAC table, right? When it knows what ports are out here. But in this particular case, the reason why the switch is going to broadcast to everybody, it's not because it has to build its MAC table as much as the Arp isn't destined to any particular device. It's saying, hey, if you have this IP address, I need you to send me back your physical address. Data is delivered from device to device using physical addresses. Logical addresses allows us to go from network to network. Okay? At this particular point, I need to talk to somebody that's local here. My switch is going to manage that, and my switch handles layer 2 addressing, MAC addresses. So if I want to talk to this device, I have to supply the switch with a MAC address. Why does the switch need the MAC address? So they know what port to send it out on, right? Because a switch likes to establish private conversations between end device and end device. We good about that? Hubs don't. In fact, I probably don't even need to send an Arp request if I'm using a hub. Even though my computer would do it, technically I wouldn't need to. Why not? Because anything that comes into a hub gets copied and sent out all other ports, correct? The only way I can have better control over that is if I add another layer of control, another type of addressing. In this case, a physical address. So my computer, when it builds its frame to be able to ship it to the switch, it's going to need a physical address. So let me hit forward. Are you going to get skinnier on me? Nope, I guess I have to zoom out a little bit. Sorry, guys. Resolution at home is a little bit different than this one. So here's that Arp request going. Now, remember I said I'm going to ping computer 20, so I typed in 192.168.1.20. We good about that? Before I can actually ping, as you can see, I'm just dealing with an Arp. It's going to send out this message, if you will, to the switch, and the switch is going to send out all other ports except the one it received it on. We good about that? What are all these other computers going to do except for computer 20? It's going to ignore it. It's going to drop it. Why are all these other computers with little red X's, and why is 20 just good with it? Because they said, look, if you have an IP address of 192.168.1.20, you need to tell me what your MAC address is, what your physical address is, correct? No two computers on the same network can have the same IP address. Hence, only one other computer on my network can have that address and should be able to respond back to this Arp request. We good about that? What happens if all these other computers were in the middle of communicating with their friends? They have to stop. They have to listen to this Arp request. They are being bothered by something that doesn't really pertain to them, correct? Why? Because if we're dealing with electricity, folks, and this is receiving data from somebody else, and the switch gets this Arp request, after it's done sending the last frame, the switch is going to send it out, stopping everybody else from communicating. Because what does the communication process entail? Sending data and also what? Receiving it. And you can't continue. This is like being on the phone with your friend and call waiting clicks through. You got to stop your conversation and answer call waiting just to resume it. What happens if more and more people are sending these ARP requests? In fact, let's not make it so specific, and let's just say, what happens if more and more devices are broadcasting across your network? What happens to the performance? Degrades. Regardless whether you're using a switch or a hub, it will degrade. And that is the chief reason why we need to break these networks up, this network up into smaller pieces, so that the broadcast is only within a particular subset. In fact, we call these broadcast domains for that particular reason. So let me hit forward, and as you can see, only this computer is responding back to the switch. Is this going to be copied and sent out to all the others?
No.
How do we handle local delivery? Using physical addresses. Physical addresses for local delivery, right? This switch knows about PC1's physical address because PC1 initiated the conversation. It came into the switch. The switch said, oh, yeah, I know you. You're port 1. We good about that? Now it sent out that ARP request to everybody else. Then we're at PC20. PC20 is actually responding to that ARP request. Now the switch knows about PC20 being plugged into port 20, if that's where I plugged it into. Would it be okay for PC20 to address only that particular device? Sort of makes sense. It should have the IP address, and that's what it does. Why should I bother everybody else now that I know PC1's IP address? And now you're saying, well, how does PC20 know about PC1's physical address? Because PC1 had to stamp it here in its frame. This is one of those things about this chapter. You got to explore other chapters to get this. We'll explore that technique in another, chapter 7, if I remember correctly, chapter 7 or chapter 8. But until we get there, I want you guys to feel pretty comfortable that the switch tries to manage individual conversations by using physical addresses. Before I can actually do that, however, I need to make sure that my Arp table on my computer is being built. So I'm going to finish this simulation by hitting forward. It should say done. This is going to view previous results. And now I have my replies. The important thing is if I come here and I type in ARP-A, I see, let me move that up for you, that the physical address for 192.168.1.20 is this particular one, 00D0. It uses a hexadecimal. A physical address in Ethernet is 48 bits. Okay. Typically, I've seen it where it's 2 digits followed by a colon, then another 2 digits followed by a colon. Cisco uses this little decimal dot notation, so they do it in groups of 4. 4.4.4. Nevertheless, it still adds up to 48 bits. Like I said, you'll explore that. We'll be exploring that in another chapter. If I go to PC20 and go to the desktop and click on Command and type in ARP, should there be an entry in this table? And whose entry should it be? The one who I received it. Folks, it's very full duplex. If I'm sending something, I got to stamp my name to the package, correct? And then underneath my name, what am I going to write if I'm writing you a letter? My street, city, state, and zip code, correct? If this is the first time you receive something from my new home, what are you going to do next? You're going to write it in your address book. Why are you going to write it in your address book? So it's there for you to quickly look up without bothering me or anybody else to get it, correct? So every computer will have an ARP table, just like they will have their own routing table, just like they'll have their own what? When it comes to resolving domain names to IP addresses. They're DNS entries, correct? We call that the DNS cache. So let's get into breaking these computers up. In order for me to break these computers up, the first device I'm going to have to do is delete the switch. So I click once, close out a dialog box, and hit the delete key. It's going to say, are you sure you want to do that? Now they're all disconnected, correct? The next thing I'm going to do is just take these devices and move them away from each other so I can organize them in a more user-friendly format. So I'm going to grab these over here. Whoops. Move them in a circle so you guys can see that this is its own private little Indian gathering. And what am I going to put in the center? Switch, because I want to create a local area network, correct? In fact, I told you a wide area network is a bunch of local area networks connected together. All right, in the interest of saving time, I'm just going to come down here to lightning bolt, hold the control key, and do the auto connect, correct? And I'll do 6 to the switch, then 7, then 9, 10, 8, and 11. Hit the escape key. I'm going to hit the fast forward time so they all lit up. I'm going to go do the same thing to the other network. Remember, this is the children network. And I'm going to do the same thing mom and dad's network. I'm going to add a switch between those. I'm going to fast forward that. You know what? I don't want to buy a separate internet connection for my children network and for my adult network. Granted, sometimes I feel like we need that, especially when they're getting into YouTube and they're tying up all the bandwidth. But what have we learned in the other chapters? What can I do about controlling their bandwidth? What's that service? Starts with a Q. Qos Quality of Service. It allows me to create policies of traffic that's leaving my network. Well, here's the catch. By using a router, setting up gateways outside of these LANs, I can set policies for each network. And I can say anything that's destined to this network here, I want you to only give it a couple of kilobits per second. Anything that's destined to this network over here, I want you to give more. In fact, I can even filter things out by IP addresses. If somebody comes into my network and they don't have the following IP address, deny them access. Not only a router helps to implement security, but I can also use something else known as a firewall to block certain applications for each of these networks. If there's certain websites that I don't want these children to access, I can set it up in a content filter. In fact, one of the things I told you guys about, and I said they are not going out of style, is maybe we can set up a hub. And off of that hub, I'm going to put in a server. It's more or less a monitoring station. Why did I choose to use a hub in this case? Because what you're going to see in a second, I'm going to add a router here and a router here, and then those two routers are going to connect to this hub. In fact, let me do that so you guys see that. So here's one router. Here's another. And then here's the last one I'm going to add to it. I'm going to connect that router to this network. I'm going to connect this router to that network. Sorry, that switch to this router. Then I'm going to connect these two routers to this hub. And then this hub to the bottom router. Why would I do something like that? And where would this router be connected to? My internet connection, right? Why would I set up a hub in this particular scenario versus a switch? Or why would I even just have one router, this router connected to that network, and also this network, as well as the internet, which I could do. This one's very costly to implement. I would get better performance out of this, and I'd also get more control. But the question comes back is, why would I put a hub right here between these three routers and hook a server off of that? Remember I told you I'd call that more of a monitoring station than I would a server.
Because the hub will send everything to the server.
So now I get to see what my kids are getting into. And would my kids know that? No. Do I have to go to any one of their computers to install some kind of parent software?
No.
My hub will do that. Because anything that's going out has to go to this server, it gets recorded, and then I get a nice little progress report from my children, if you will, without them knowing it. Do you think that happens in corporate America?
Mm-hmm.
Absolutely. Yeah. Do you see by breaking my network up into smaller pieces, I have more control over it? I can assign better policies so I can blanket one group, one purpose. So this could be like my HR people, this could be my faculty, this could be students, this could be administrators. And I can set different different levels of security. You know, the other thing it allows me to do is it allows me to keep data within this. And if it's closer to this network, it should do what? It should perform a lot better, correct? So if my kids always want to watch movies and I don't have to change the DVDs, maybe what I can do is put a media server onto their network. And it's going to contain that traffic, that bandwidth here, locally. So the video should load faster. They're not going to argue, oh, well, so-and-so's got the TV if they all have their own iPad. By storing our movies into one central location, by taking our DVDs and ripping them and putting them on our server, each kid can watch the same movie at different times, at different parts, without bothering our network. This is just an example of how you can take a network and divide it up by purpose, implement security, and get better performance. The key thing here is security and performance. I'll see you guys tomorrow. We'll get more into this. We'll talk about the IP structure and how it's actually implemented.